All right, okay. So yeah, so I was thinking about doing a kind of board talk today about reactive synthesis. I know a lot of you might. How many of you already know what reactive? Okay, good, good, good. So it's not like too many. I can use this, right? And then I can use that for erasing. All right, so the first lecture that I was talking about was mainly about human-robot interaction. So we've already talked about like how we can have human-robot systems, like humans and autonomous systems. So let me actually write that here. So we talked about human-robot systems. So this is basically a robot interacting with a person, and we care about like building good models of humans. So we kind of talked about that like last lecture. And we can call these human-robot systems human CPS too, if you really want to call things cyber-physical systems. They're kind of the same thing. Can I erase this part? Is that OK? Yeah. So we started talking about this overview lecture of what they are. And we talked a little bit about human modeling. So that's one thing that I wanted to talk about at some point. So we talked about this approach called inverse reinforcement learning, or learning from demonstration. The idea was I'm going to gather a bunch of trajectories, and from those trajectories, I want to recover what is a cost function. So if you have time in the third lecture, I might talk about that, like talk about like how we build good computational models of humans that can actually be useful when we talk about planning or synthesis. And then I talked about modeling interaction a little bit. So modeling interaction. So we talked about that in a kind of two-player game setting, where we have like a robot and a human working together, actually affecting each other. We had this nested optimization that was kind of difficult to solve, but we were trying to basically come up with approximation algorithms to do that. I want to talk a little bit about safety, so that's the point of today. And for that, I want to talk about reactive synthesis. Yeah, mainly reactive synthesis. So we talked a little bit about this. Maybe third lecture would be about human modeling. Today we want to talk a little bit about safety. So why do I care about safety, or why am I like talking about reactive synthesis and I talk about safety? So I'm coming from, actually I have like a formal methods background, but then in grad school I was doing a lot of control theory and robotics. And I'm coming from the control theory perspective of why we need safety. So in control theory, at the end of the day, you want to design a controller for your car or for your airplane. Like at the end of the day, you want to figure out what is that control. So actually, when you talk to like a lot of control theorists, they don't really they care about model checking, but they don't understand the point of model checking as much. Because at the end of the day, they're like, how do I find that controller? How do I find that policy? And you have to like give them a way of figuring out what that policy is. And reactive synthesis is trying to address that problem, trying to figure out what that policy is. So it's kind of a powerful idea, and like control theorists really get excited when you tell them what reactive synthesis is, because they're like, oh, provably correct controllers, that's going to be awesome, like that's going to solve all our problems. So they get very excited about the idea of reactive synthesis, and because of that, actually there's a lot of research like at the intersection of control theory and formal methods where people are looking at this specific topic, because the promise is it's going to give us provably correct controllers. So if that was the case, that would have been really good. But there are issues. There are issues, and because of that, it doesn't like work as well. But the idea is kind of powerful. So that's why I want to talk about reactive synthesis from linear temporal logic. So that's the goal of today, right? Plan makes sense? Let me actually keep track of time, so I have till 10 probably. All right. So what does that mean? Like when I say you want to talk about reactive synthesis? So the idea is you're going to have a specification. This specification could be written in linear temporal logic. So let me write temporal specification, temporal spec. And then what is a reactive synthesis of a system? So first off, we need to know what we mean by reactive system. So reactive system is basically a system that gets an input. So this is our system. That gets inputs, and in real time, like synchronously, it's going to provide an output for every single input that it gets. So it gets inputs from the environment, and it reacts to that input and provides a set of outputs. So at every state, as it gets an input, it produces an output synchronously, and it's also non-terminating. So the type of questions that you want to determine or want to figure out the answers are is that does there exist a finite state system or a finite state controller that's going to satisfy a set of temporal logic problems? So that's kind of the main goal of reactive synthesis. And if that system exists, if there is a finite state kind of system that I can put in here, can I construct that just from the specification? So if you remember the model checking problem, the idea is you get a model, you get your system, you get your finite state system, and you have specification. And the output of the model checker is kind of a yes/no question. Right? Like it tells you if your model satisfies phi or doesn't satisfy phi. But reactive synthesis is a little bit more powerful in the concept in some sense, right? The reactive synthesis, what it does is, that it only gets the specification, and then it's going to output a model that satisfies the specification. It's kind of like magic. Like if you tell someone this is what it's going to do, it's very like you just tell me you want safety, and I'm going to come up with a model with a controller that satisfies your safety specification. And then last night you were talking about learning. Like you were talking about, well, how is this different from learning? So in learning, so at the end of the day, I have a model, right? Like here, I have a model that it gets inputs, and then it gives me outputs. In learning, the thing we don't have about the model is specific parameters about that model. And we try to learn that from data. So the picture that we have when we do learning, machine learning, is I don't know something about my model, and I'm trying to learn that from data. And then at the end of the day, I'll get this model that if it gets an input, it provides an output. So the picture is a little different. In reactive synthesis, we start from specification, a very formal, logical thing. In learning, we start from some data. And like by looking at input-output sequences, I want to learn the specific parameters of my model. So that's kind of like one big difference, like when we think about these two systems. Okay. All right. OK, so that is our goal. If you think about the history of when that started, I have like a few slides, but I don't really want to go over the slides. So the history of it started with Alonzo Church. So there was a summer school. And then from that summer school, like this was in 1957, and Alonzo Church came up with the synthesis problem. So it was about circuits. And the synthesis problem is to find recursion equivalences representing a circuit that satisfies the given requirement. So given requirement is my specification. I want to figure out a circuit that satisfies that given requirement. So it started with, so let's do a little bit of history. So Church kind of introduced the problem in 57. Then at some point, Buki and Landweber started thinking about the problem and providing kind of a game view of trying to come up with solutions for this. So they talked about reachability being decidable, and they talked about if a winning strategy exists, then a finite state winning strategy exists. So again, like you're trying to figure out if there's a finite state system that I can build. So they showed that if there exists a winning strategy, if there exists some strategy, it's definitely going to be finite state system. And they had like a game view of the problem. So in 69, they provide this game view of the problem that we'll talk about. Then 72, Rabin came up with like simpler solutions. And then more recently, so let me just write the more recent stuff. So Amir Panuli and Rosner in 89 talked about Ltl synthesis. So specifically, if I'm starting from specification that's written in the linear temporal logic language, how would I come up with a model? Okay. All right. So and that's the main thing we want to talk about today. So just a few formalisms. Maybe I can just show that on this slide too, so I don't need to write it right here. So the formalism that we have for reactive synthesis is we have this system and we have this environment that are in some sense playing against each other. So we have a set of input values, a bunch of inputs that are coming. So we have a set of input variables. Let's call those i's. We have a set of output variables. Let's call those o. And then the system, so the system is not the same system idea that we hear in control theory. The system is actually playing against this environment. So the system is choosing its outputs from all the subsets of O, and then environment is choosing all its inputs from all subsets of I. And then we really have this infinite play. Like if I get an input, I provide an output. Next input, I provide an output. So I have this infinite behavior of unions of I's and O's. And I have a specific behavior, like after seeing this infinite behavior, I have an infinite behavior. And what I want to check is I want to check if that infinite behavior satisfies some specification. That specification could be a linear temporal logic specification, over my sets of inputs and outputs. And the thing we are looking for in reactive synthesis is this model or this strategy. So you can think of this, like the thing that goes in this box, as that strategy, that function that takes me from the input sequences to output sequences. So what that, like when we say provably correct controllers, what that means is if you provide any inputs for me, I know what output to produce, so it satisfies my specification. So that's why it is powerful. Like no matter what input you give to me, whatever environment decides to do, like I know how to respond to that, so I can satisfy my safety specification, let's say, or whatever other specification I have. Okay? Like I have an autonomous car. And no matter whatever it sees in the environment, all sorts of like ways of traffic lights or like environment situations, if I can come up with that strategy, I have a strategy of set of accelerations and steering angles, so it's going to be safe. Like that is kind of that is why control theorists like get super excited about it. Okay. All right. So and there's kind of like this. So this for all there exists kind of idea is called realizability. So there's actually a difference between realizability and satisfiability. So reactive synthesis is trying to solve the realizability problem. So let me first say so in satisfiability, if I want to say M satisfies some phi, what that means is there exists a set of inputs I0, I1, I2, for which there exists a set of outputs O0, O1, O2, so on, so that the infinite behavior is going to satisfy phi. So this is satisfiability. Reactive synthesis tries to solve the realizability problem, which is harder. And it checks if for all input sequences, I0, I1, I2, so on, there exists an output. And it outputs that. So that is why it is kind of more powerful. No matter what you provide, it is going to output the problem and the solution. All right. So now let's talk about specifically how we can do reactive synthesis from linear temporal logic. So how many of you know linear temporal logic? All right. So quick overview, I guess, very quick overview. So linear temporal logic is just a specification language, and it has 4 main temporal operators. And what that means is linear temporal logic, what that means is if we have a sequence, a time sequence of my system, I can talk about properties over this time sequence. And one confusing thing, again, talking to control theorists, is when you say linear temporal logic, they immediately say, well, what is the linear part? Like, where's the linear system, like here? There is no linear systems here. Like, when we say linear temporal logic, what that means is it's over a linear time. So it's over one sequence versus having like multiple like time sequences like going together, like having parallelism in some sense. We have one sequence of time. And then the 4 main properties, which are like the only things like you should remember like for the rest of this lecture, are these 4 temporal properties. One is, we say globally phi, where phi is this Boolean that can either be true or false, let's say, over my sequence. And if I say globally phi, all that means is phi is true at every time step of my sequence. Okay? People write it with squares too. So you can write square phi, which is the same thing. I don't like squares because they're not intuitive. G at least means globally. You remember that it's going to be true at every time step. You can also have eventually phi. So eventually phi is kind of a good abstraction of saying like phi is going to happen at some point in the future. I don't know when, but it's going to eventually happen at some point in the future. So it's not telling us a when, but it is telling us somewhere in the future we'll see phi. We have next phi, and what that means is wherever I'm starting at the next time step, I'll see phi. And then we can have phi1 until phi2, which means that I'm going to see phi1, and at some point in the future, maybe I'll see phi2. Okay. So I have these 4 main kind of temporal operators, and I can use the rest of kind of Boolean operators to combine them and come up with interesting properties. So the cool thing about it is you can actually come up with very interesting properties here. You can combine them, and let's say if you combine f and g, Like you get two interesting, like I'm just going to write two interesting ones. So we can write future globally phi. So what does future globally phi mean? Intuitively.
Eventually it will hold.
Yeah, so it's kind of like stability, right? Like I'm starting from somewhere, and at some point in the future, phi is going to hold, and so on, right? So again, in controls, you have notion of stability. So when they see something like this, they're like, oh, that's stability. That is cool. Like if I can prove stability, which is, it's very different from the control theory way of talking about stability, but it's another notion of I'm going to have some sort of stability. There's another notion called globally future phi. What does that mean intuitively? Yeah, so infinitely often I'm going to see phi. There's always true, at wherever I am, there's always true that at some point in the future I'll see a phi. And now I'm here, and then it's always true that at some point in the future, I don't know when, but at some point in the future, maybe I'll see phi again, and so on. So what that means is infinitely often I'm going to see phi. Again, why do we, like robotics people care about this? This is kind of like a surveillance property. If I have a robot that wants to visit different sides of the room infinitely often, and I don't want to give it a schedule because I don't want people to figure out like when it visits different sides of the room, I can write that with like globally future phi. It's a surveillance type property. And you can write other types of properties, but the whole point of it is you can write these like higher level, like interesting things you care about in linear temporal logic. So it's a powerful language to start with when we think about designing controllers for. All right, so I want to talk about reactive synthesis, but I want to just give it, kind of do that through an example of how we can start from a temporal logic specification and then come up with this model or controller. But I just want to do that through an example because that seems simpler. Otherwise, it gets too complicated. And the example I want to actually talk about is the coffee machine example. I'm sure a lot of you have seen this. OK, so coffee machine example. Let me erase this first. So let's say we have a coffee machine. Seems important. And we have that English specification about our coffee machine. So what does it say? So it says if the start button is pressed, then the system, the coffee machine, will immediately start grinding for the next 2 cycles, and then it starts brewing for the next 2 cycles after that. And then after that, we'll have coffee. So the first thing you would want to do is you would want to actually write this in a temporal logic language. So how do I write this in linear temporal logic? So it says if the start button is pressed. So let's figure out what our inputs are, what our outputs are. Right? There's an input into there's a coffee machine, so it's a system. It's a reactive system. It gets an input and it produces a bunch of outputs. So the input it gets is just a button. Right? That's the only thing I can do. So my set of inputs is just button. I can either press it or not press it. So button's either 0 or 1. And then what does it output? Sure. But from this kind of sentence, it can do, so it can grind, or it can do something else. Brew, right? So like we can say at every point in time, it is either like grinding or brewing or none of them. So both of these are, again, Booleans, right? Like it's grinding could be 0 or 1, brewing could be 0 or 1. What's that? Will be produced. So that part I'm ignoring it. Produce. Let's say that it can only like grind and brew, and if it doesn't do any of them, like coffee is produced now. We'll be happy after that. So if I want to write that in like linear temporal logic, one way of writing it is, well, when we say if something, we usually need to put like a globally outside because it's true at all times. If I see something, if I see what? If a button is pressed, then something else happens. So far, so good. Globally, if a button is pressed, then something happens. What does it happen? Well, it's going to grind at that step. And then it's going to grind at the next time step. And then its next time step, it's going to brew. And it's done grinding, so it's not grinding. Sorry, next time, the time step after that. So I'm going to use XX to talk about the next time step. And then after that, it's brewing for 2 cycles. So after that, it's also brewing and not grinding. So this is my specification. I have an English specification. I can write that in linear temporal logic. And what I want to do is I want to figure out, the first thing I want to figure out is if it is even realizable, if this even exists or not. So like there are two questions, right? One is, does this M even exist? The other question is, if it exists, how can I come up with it? And I want to check first, like, if it exists or not. And I'm, again, like for this one example, I'm just going to do it a little bit intuitively. So let's talk about first satisfiability, right? Satisfiability was saying there exists an input for which there if there exists an input, if there exists an input for which there exists an output, so the sequence satisfies the specification. So I can look at kind of a sequence. Let me write my sequence. My sequence is my sequence of input being button. I'm going to write kind of a tuple. And then let's say output is grind. The first one corresponds to grind. The second one corresponds to brew. Right? So let's say that when I start, like I don't press anything, so there is no grinding and there is no brewing. And let's say next time step, I'm pressing a button. So if I press a button, this is going to become 1. How about these? 1 and 0. Okay. How about next time step? Let's say I don't press anything, so what happens here? Here? And then next time step? And then for 2 steps, I am doing this, and this can like goes to 0, 0. So is this sequence satisfiable? Does it, by satisfiable, I mean, does it satisfy this? It does, right? So I just came up, okay, I'm going to erase this. So I just came up with a set of input sequence for which there exists a set of output sequence. And the two together, like the combination of the two, satisfies my specification. So let's look at another example. So the other example I want to look at is, let me do it here. So let's say I have the same sequence. Let's say that I start from pressing a button. So if I press a button, then I get grinding, and I get not brewing. And let's say in the next time step, am I doing this right? Yeah. So in the next time step, I am going to press the button again. So I'm pushing the button twice. What do I get here?
Oh, it's still 1, 0. No conflict yet.
No conflict yet, right? Like it's still 1, 0 because I got to be grinding for this past one. I'm also grinding for this one, so it has to be 1 for grinding. I'm not brewing anything because I'm not there yet. And then next time step, let's say I'm not pressing anything. The input doesn't matter here, right? So, and for this guy, like for this press button, I have to be brewing here. But what should be this one? What should be the grinding input? Yeah, it's not specified, right? Because like we don't, like if I go with this pressing, it should be 0. If I go with the second press of the button, I should make this 1. And because of that, we kind of have this situation where there exists, not there exists, not that, it's not the fact that for all inputs, there exists an output for which we satisfy the specification. So this particular specification is satisfiable because I can find a sequence of inputs for which there exists a sequence of outputs, and together they'll satisfy the specification. But it's not realizable, and then why is it not realizable? Because I just found a sequence of inputs, 1, 1, 0, for which I cannot come up with a sequence of outputs that satisfies the spec. Okay? So realizability is basically trying to check, does there exist even a strategy? And it doesn't exist. Like for this case, it doesn't exist a strategy where we can find this finite state system that would satisfy the specification. So this was just kind of like an example to show, like it's not necessarily the case that we would have realizability all the time. All right, so now that we've seen an unrealizable example, I think it's time to talk about actually how we would do reactive synthesis. So let me erase this. This board is kind of tiny. That's not feasible. Sure, I'll turn. but then they can't see it anyway. Can I erase everything? Is it okay if I erase everything? Okay, I'm going to erase everything because I want to like show an example where we want to do reactive synthesis. And this is actually the magic part. So like every time, again, control theorists really like this idea. And every time they read formal methods papers usually say, yeah, there'll be game, we'll solve it, it'll be awesome. And they have a hard time like figuring out what is really the magic that goes like underneath it, because like no one really talks about it that much. So I want to talk a little bit about that magic part. And again, it's just through an example. It's not general. I'm just going to show it through one example how we can come up with a finite state strategy. So our goal is still doing this synthesis problem, right? I have the spec. I want to do reactive synthesis. Reactive synthesis is going to give me a model or is going to give me a strategy that goes from, or strategy that goes from a set of inputs to outputs. And then if it gets inputs, it produces outputs. And M hopefully satisfies phi. This is my goal. Okay? And let's just do this through an example. So let's say that I have a specification. So I have a specification in linear temporal logic. My specification is, let's say, globally, if I get a request, next time step, I'll grant it. So I didn't define my input sequence. So let's say my input is just getting a request or not getting a request. And then my output is granting or not granting. So that's my input sequence. That's my output sequence. My LTL specification is a specification over the inputs and outputs. So if at all times, if I get a request, next time step, I should grant it. That's what it's saying. Okay. So the kind of pipeline of doing reactive synthesis is we start from a linear temporal logic specification. And the first step is to create a word out of this. So there is a transition that we go from linear temporal logic, and then we create a word automaton. Word automaton. Specifically, a non-deterministic bool keyword, let's say. So this transition, again, I'll not talk about the general case, but let's see like how we can actually go from this particular input and create this word, this state machine type thing. So what this is saying is, if I'm in state, right, and in that particular state, let's call that Q0. Let's say that's the state I start with. If I get a request, I should go to a new state. If I get a request, I'm going to a new state. And this is my granting state, right? Next time step. So I go to the next time step. So this is time step 0. I get a request, and I go to the next time step. And right here, what should I do? I should grant it. What happens to my R? How about R? So it could be two cases, right? It could be the case that I'll get an R, and I grant it, and I stay in the granting state, because even if I get an R in this time step, I got to be granting it. So this is the granting state. Or the other thing that could happen is I don't get any request the next time step, but I'm still granting this one. Let me just make sure I'm not messing that up. Right? So if I'm at Q0, I get a request. It could be the case that I get a request. If I request it, I go to a granting state. In the granting state, I have to grant whatever I do. But what could happen is I could get another request, so I can stay in the granting state and then and get a request and keep granting. Or I could go back to this Q0 in some sense, and I don't have any requests here, but I'm granting this last one. And if I don't get any requests, then I just like stay here. Okay? So everyone agrees why this is kind of writing that, right? So this transition, by the way, takes exponential time in the size of your specification. So we have kind of an X time blow up already here. So the next step is, OK, so now I have a non-deterministic bool keyword. And if I have a non-deterministic bool keyword, I have to determinize it. In this case, it's actually not like really non-deterministic. You have like deterministic transitions. But if usually, like if you end up with this non-deterministic bool keyword, the next step is you want to create a deterministic tree out of it. And I'm going to call this deterministic parity tree. We'll talk a little bit about that. And to determinize, kind of the step to do is you have to take this step, taking this non-deterministic system and determinize that. And there are ways of doing that we are not talking about. But there are ways like subset construction, and there's like, let me actually write those. So these are not things you're talking about, but you can do things like subset construction, or there's like this other algorithm called Safrollis algorithm that Orna Kupferman and others kind of came up with at all. So you determinize your system, and that determinizing also takes exponential time. So we are already at a W exponential time algorithm, which is pretty bad. And then after having this, in some sense, you create a game between your environment and system. I'll create that game in a second. And then you solve the game, which is polynomial time, with whatever winning condition you have. So this is polynomial time. And you get a strategy. Strategy being that f function. So this is kind of the pipeline of doing linear temporal logic synthesis. You have a specification, you got to create a word out of it, that takes exponential time. You got to determinize it, that takes another exponential time. Then you have a game view of the system, and you can solve that game and get a strategy. So let me actually create that game view of the system, because we don't need to do any determinizing here. So now I have this word automaton, which is over both inputs and outputs, right? I have R and I have G's here. And to create a game view, what we want to do is we want to separate those out. We want to separate inputs and outputs, so we have kind of this two-player game between my inputs and outputs, like playing against each other. And to do that, we'll create these intermediate states. So that's easier. So I'm going to just write a game view of the same word automaton. And the game view is I'm going to start from Q0. Then my environment is playing. So it's my environment playing. My environment can either provide a request or does not request something. And then I'm going to these intermediary kind of states, because I don't know how the system is going to respond. Because it's environment's turn. Environment can either request or not request. And then if you are providing a request, at this time step, environment could do anything. We don't really care. Like this is the very first time step. Like environment could grant or not grant. That doesn't matter. And then we end up in Q1. And similarly here, we don't really care. And we kind of see that here, right? Like we don't really see a G here or here, like on these transitions. So what that means is it doesn't matter if I get G or not G at the very first time step. So we don't really care there. And now we are at Q1. So again, environment's turn. Environment can do two things. Environment can provide is that a good way of writing it? Yeah. Can either provide a request or not request. So environment's turn. We go to intermediate states. If environment provides a request, well, what should the system do? Should be granting. Right? So the system grants. Okay. If we don't get a request, I should still grant this past request and go back here. So I'll go here. So far, that's kind of very similar to this thing. I just created these like intermediate states to create this game between input and output. But we should also have these like unsafe states in some sense. And these unsafe states are really when we are not granting the request that we should be granting. So if it turns out that I'm at Q1 and system is not granting, then that's pretty bad, right? Because we want the system to actually grant. And if the system is not granting, we're going to this other state that is this unsafe state that I should not be falling in. So my specification was globally at all times, if I get a request, next time step I should grant it. Globally, if I get a request, next time step I should grant it. And if I ever fall into this unsafe state, that is the only time that I'm not satisfying my LTL specification. So again, intuitively, I'm like not talking about too many details here. Intuitively, if I want to satisfy an LTL specification, if I can actually create this game, I can just make it a reachability game and make sure I never visit this. And how can I do that? Well, I need to figure out a strategy. I need to figure out how the system should respond so I never fall into this bad state. How should the system respond? Can someone come up with a strategy? Just one strategy. So I need to extract a strategy from this.
If Q1, then always grant.
Always grant,
Or
yeah.
just always.
Always grant, yeah. If I always grant, that's a strategy, right? That is a thing that system could be doing, always granting. And that's pretty good, because if I always grant, if I'm here and I grant, I'm granting here. Actually, let me write that strategy. So if I want to write that strategy in this form, is if I don't get any R, I'm granting. I'm always granting. If I get an R, I'm granting. At that very first time step, we are starting and we are just granting. And then we are in Q1, and then if we get an R, we are granting. And if we don't get an R, we are granting too. So this is my strategy. System strategy. This is the output of my reactive synthesis algorithm. And from this game view, what I can do is I can extract a strategy so it never visits the unsafe state. And I've now satisfied my specification. So that is pretty powerful, right? That's a provably correct strategy. That's a provably correct controller. You can think of it as a controller, because whatever it sees from the environment, it knows how to respond. The way it's responding is I'm always granting. And with that particular way of responding, it never sees the unsafe states. And we just did that through this kind of approach. The caveat is it's a doubly exponential time algorithm. And doubly exponential time is pretty bad. But one thing to notice is it's doubly exponential in the size of your specification. So if your specification is not that large, it's not too bad. Yeah? All right, so this was a very simple example I showed. So I want to actually show you a more complicated example. Do I have time to show? I have 2 minutes. I still want to do it. OK, so I want to just change this a little bit to show you that it's not as simple as what I've shown on the board. And what I want to do is I want to actually change the specification. So it is globally, if I get a request, instead of next time step granting it, I make this eventually I grant it. OK? So then creating this word automaton is actually not this simple. The word automaton I'll end up in is going to look like something like this, where I'm in state. It's an accepting state. If I get a request and I'm not granting anything, I go to this waiting state. And I'm waiting there, and I'm not granting anything as I'm waiting there. And whenever I grant, I come back to this particular state. And in this state, this is kind of the happy state where I don't get a request or I'm granting. So I didn't really talk about how I created that automaton, but you can take this LTL and you can come up with this particular automaton, which is a little different from here. I have this kind of accepting state here, and I have this wait condition where I'm not granting, I'm waiting, and the moment I grant, I go back to this happy state that I can stay there infinitely often.
But shouldn't you have an accepting state also for the first one?
For the first one, in some sense, yeah, Q0 is accepting. Yeah, so it's not the accepting part of it that, it's kind of the infinitely often you want to be there part of it that I'm trying to focus on. So it's not always that you end up in a game where there's just an unsafe state and you just want to avoid visiting that unsafe state. For some specifications, you end up in a game where the winning condition is actually very different. The winning condition is not a safety game. It is actually something more complicated that tries to visit some states infinitely often. And those games are harder not harder to solve, but they're not as simple as this, right? The transition to them is going to be more complicated. And it turns out that you cannot necessarily go to a safety game from any LTL specification. From an LTL specification, you can go to either a non-deterministic bool keyword, so you have that non-determinism, and you have this Buki condition. So Buki condition is I'm going to visit my good states infinitely often. Or you can end up in a deterministic parity game. So that's kind of a level more complicated. And the winning condition for parity games are just going to be, again, a layer harder than Buki games. So in Buki games, you want to visit a state infinitely often. In parity games, there are good states and there are bad states. And you want to visit good states infinitely often. But you want to make sure you're visiting the bad states only finitely often. So that was a little too quick, but maybe like next time I'll briefly talk about this before talking about the human modeling side of things. All right. Any questions?
What is it that complicated in LTL is to see what the formula really means. For example, if you change the next to finally, then you release at the same time the condition that each request is uniquely responded by a grantee.
Yeah.
And this is really makes sometimes complicated also if people try to use in industry who are not well educated in formal methods, especially in temporal logics.
They can think they're the same thing.
To see those differences.
Yeah. Yeah, and then they create like so much more complicated situations,
Yeah.
like when you add eventually there instead of next.
And actually, I think in LTL you even cannot express that each request is uniquely answered eventually by a grant.
Yeah, because it's just eventually you can get request, and then like
Yeah.
grant, and that's perfectly fine too, right? Yeah. Yeah. Yeah, it is interesting. It is interesting. Yeah.
So, what about the true stability?
Mm-hmm.
How do you expect to deal with
Like
convergence properties?
Yeah, so I'm not familiar enough with it, but I've heard a talk from, I don't remember from who even, but I've heard a talk where they show actually the stability, like the convergence stability we see in control theory is not equivalent. Like you cannot even represent it in like linear temporal logic. So they're quite different like notions of stability. So yeah, so you can't represent everything necessarily in linear temporal logic. So this is like a subset of things. I don't remember who gave that talk, but there was like a specific, there's a paper about how they were very different.
But like the practical stability, I imagine that it can be possible, like for example, how convergence towards some attraction
points, yeah. Yeah, so like we can do these combinations of future globally, like some specification, and we can do all this whole thing and create the automaton and solve it. The other problem that exists is that again roboticists don't realize at the beginning because they're like, oh, like probably correct controller, is there's a lot of continuity, like, and this is like a very discrete kind of idea. You have like this game, the two-player game between a very discrete system and another very discrete system. And in robotics, everything is just inherently continuous. Like you either need to like do little like tiny like discretizations and do some sort of bisimulation, or like you cannot use any of these methods. And you can do the bisimulation approach, but it ends up, because it is doubly exponential, it ends up becoming like not as practical as people hope it would be.
And I think also another problem is that not each output can be generated at any time.
Yeah, not each output can be generated at any time. Yeah, you can put that as a constraint though, right?
Yeah, but then you end up at the same problem. Formulating all constraints is
it's not, yeah,
in
that's
a
also,
discrete manner.
that's right.
It's not so easy.
Yeah.
Any other questions? Great.
All right.
Thank you very much,
No
Dorsa.
problem.